Alrighty, so in class today, we moved forward and started talking, instead of just about those moments where we have a temperature change during heat transfer, looking at what happens if we also have a phase change going on. So we revisited this freezing and boiling point graph, or this heating curve that we looked at in ALT1, to kind of identify those regions, right? Where is it a solid or a liquid or a gas? When is it melting or freezing, boiling or condensing, to kind of get our heads around that. Then we looked at an example problem, right? We had some ice, and we realized that you can't do a simple Q equals MC delta T calculation for the entire transition, because as you see in the upper right-hand corner, my little heating curve shows me that it's not just a simple heating problem, right? I start by heating up a solid, then I change phases by melting, then I heat up a liquid, then I change phases by boiling or vaporizing, right? So what we saw was that a substance, while specific heat capacity is an intrinsic property, state matters. So ice or solid water will have a different specific heat capacity than liquid water would have. So we need to look at this heating curve, figure out how many different line segments we have essentially, and then that'll tell us the number of little Q calculations we have to do to find all the little pieces of heat that are used throughout the transitions that we can then add up to get our Q total. So we see here in this example, we start as a really cold block of ice below freezing, and we end at steam right at the boiling point. So just after it vaporized, so it is still 100 degrees. So for this, we have 4 Q values, right? Q1 is where we're heating up our solid, Q2 is where it's melting, Q3 is where we're heating the liquid, and Q4 is where it is boiling. By plugging in the appropriate mass, just the mass of our sample, the appropriate constant, either the C value of the substance at the appropriate phase, or the enthalpy of fusion or enthalpy of vaporization, that delta H value, okay? So by plugging those in, temperature change if needed, getting those temperature changes correct with sign and all of that, we get a total of 15 kilojoules-ish. So notice the math is not hard. It's just not. It's very straightforward algebra. The tricky part is making sure you do all the right math, making sure you do the correct equations, use the correct constants, and for all of that, again, it's just getting organized and paying attention to where you are on that heating curve. Then I wanted you to do number 1, or just at least to look at it, right? And so we looked at this idea of kind of the hardest possible one we could do. I did not finish the calculations, but you guys did. So, right, we saw in this example, and this is off of the extra worksheet I gave you guys, we would have 5 Q values, right? Because we're starting with a solid below its freezing point and ending as a gas above the boiling point. So this time we have 5 Q values. Heat, change phases, and then heat again. So we get a Q total of whatever it is, almost 8 kilojoules or whatever. Then I said, okay, well, then how could we calculate the specific heat capacity of whatever metal it was that was responsible for giving all of that heat to the chlorine gas? So I said, hey, we actually did this by dropping a 100-gram piece of metal that was at 500 degrees C into the container with the chlorine gas. So again, using those ideas of calorimetry and assuming that perfect heat transfer, what is that specific heat capacity of the metal? So for this, we needed to, again, understand that idea of Q equals negative Q, right? The heat of one side of a heat transfer is opposite, but the same number, to the value of the heat on the other side of that heat transfer. So the heat that went into the chlorine, that positive heat value, is the heat that would have left the piece of metal, or the negative heat value that we see on the bottom of the page here. Then again, we just do Q equals MC delta T and solve for C. Okay, so that's kind of as complicated as these questions are going to get. So keep working through the rest. Remember, I said I for sure wanted you to do number 4. So make sure that that gets done. And we'll see you next class. Don't forget to get your lab turned in.